Welcome back to Enzyme Inhibition. This time, we will discuss the inactivation of enzymes by irreversible inhibitors. To get the most out of the videos, I recommend that you watch them in order. This is a reminder that this presentation is Dr. Johnson's intellectual property. Irreversible inhibitors include compounds that mimic the transition state so well that they bind very tightly in the active site and are extremely slow to dissociate. While technically not irreversible, they behave in this way. Compounds that react with the active site to form slowly reversible covalent bonds are sometimes put in this category as well. Truly irreversible inhibitors are ones that form covalent bonds with the enzyme that are not reversible. The earliest of these types of inhibitors were used as affinity labels, reactive compounds that react with exposed active site and other residues to show which ones are on the accessible surface of the enzyme. More recently, enzyme-activated irreversible inhibitors have been developed. These compounds are generally not reactive. However, they carry a latent reactive group that is converted to an extremely reactive, often electrophilic group by the catalytic action of the enzyme. Reaction between these activated inhibitors and the enzyme results in the inactivation of the enzyme and destruction of the inhibitor. These inhibitors are commonly called suicide inhibitors. Inactivation of the enzyme has the following scheme. The enzyme and inhibitor form an EI complex with equilibrium constant Ki. The EI complex undergoes reaction to form a covalent bond with rate constant Ki. The rate of enzyme inactivation has the same form as the Michaelis-Menten equation. There are a number of different ways to determine the equilibrium constant and rate of inactivation. At the heart of these methods is the fact that inactivation is time-dependent. You can see this on the graph on the left, where ln of V0 is plotted as a function of time. The different lines on the plot represent different concentrations of inhibitor. The horizontal line has no inhibitor present and represents full activity. If we measure the time to reach half the initial enzyme activity, we have the value for the half-life of inactivation at each inhibitor concentration. We will plot this value as a function of inverse inhibitor concentration. Now we can determine the Ki from the negative inverse of the x-intercept. This represents the inhibitor concentration that will give half the maximum inhibition. We can determine the inactivation rate constant from the y-intercept, which is ln 2 over Ki. This value is the maximum rate of inactivation. This concludes our discussion on enzyme kinetics and inhibition. We discussed different types of reversible and irreversible inhibition with a focus on 3 types of reversible inhibition. We looked at graphical solutions to obtain the inhibition constants. We also discussed product inhibition and how we could use it to determine the binding order in sequential bye-bye reactions. Thank you for watching. If you found these videos useful, please like, share, and subscribe. Our next video series will be regulation of enzyme activity.